Good morning, this is Dr. Turner for Integrated Math 3. Today we're going to be talking about 1.4, which is titled Change in Dimensions. So this is looking at two-dimensional figures, and it can be three-dimensional figures as well. But we're primarily focusing on two-dimensional figures in our class and seeing if a dimension or a measurement is changed in a shape, how that affects things like the area or the volume. So let me give you an example. If I give you a rectangle, let's say this is my rectangle, we know that the area formula is defined as area equals length times width. Right? So the question or an example might be, well, if I take this rectangle, what happens to the area doubled? Now, seeing this visual might help you, might not, but if I take that length and double it, because area is the amount of space, you might be able to deduct, well, you know what, because the length is being doubled, right, then the area would be doubled. That should make sense intuitively. In terms of the formula, right, it doesn't matter really what the length was originally. I can leave this as LW, but if I take my L, and let's say I change that to 2LW, then when I'm comparing this formula here, my new formula with twice the length to the original, I should be able to see that indeed the area is twice as big. Okay? That's going to be true for any change in dimension where there's no exponent involved in the formula, right? So similarly, if I asked you what happens to the area if the width is doubled. So let's say I change this to, instead of length, I change this to width. It's going to be the same process that, again, if you want the visual, maybe that helps. I can kind of see that that's taking up twice the amount of space. And so in terms of area, in terms of the formula, if I plug in L times 2W, rearrange that a little bit using my commutative property, indeed, it's twice the area of the original shape. That's not always going to be the case, especially when we look at shapes that have a curved surface. So for instance, if I have a circle, my area formula for a circle is pi times radius squared. And I'll go ahead and just write that out on my equation editor here. The area formula for a circle, which all of those are on your formula sheet, pi r squared. So if I took a radius, and let's say, again, I would give you an example. What happens to the area if the radius is tripled? Well, because we just saw an example where the number or the value change was the same, most students would be inclined to say, okay, well then, if the radius is tripled, then the area is tripled, but that would be incorrect. Again, visually, if I triple that radius, if I'm making it 3 times as wide, you should be able to see, well, you know what? No, I can't fit 3 circles in there, right? There's a lot more space being taken up in that giant circle. So then we need to look at it in terms of the formula. So if I look at my formula, area equals pi r squared, and the radius was tripled, well, that means that the radius is being changed by a factor of 3. And anytime you have any value in an exponent, this would be like your power of a power rule, right? You have to raise everything inside the parentheses to the second power. So this would be pi times 3 squared, which is 9, times r squared. So this area is 9 times bigger, not 3 times bigger. Okay, so that's a very important distinction to make. Okay. And the same is going to be true if we're looking at a shape that's getting bigger or getting smaller. So for instance, if I give you, let's say we do another circle, and I tell you what happens to the area of a circle. What happens to the area of a circle if the radius is changed by a factor of 1/2, right? So changing the radius by a factor of 1/2, it's getting smaller. That doesn't mean the area is getting smaller by a factor of 1/2. So again, looking at that original formula, a equals pi r squared. If the radius is half of what it originally was, then that's half of the original radius. Again, doesn't matter what it is. Let's say half of the radius. And then I go to calculate that. Well, 1/2 squared is 1/4. And then I would move that 1/4 in front. So even though the radius was halved, the area is being reduced by 1/4. Okay, so it's important to pay attention to those. Again, anytime you're plugging into a variable that has an exponent, then it's not going to be the same change. Whereas if I plugged into a normal exponent, like we saw with the rectangle length and width, then it's going to change by that factor. Be careful. Obviously, you could have a shape like, let's say, a cylinder, right, that has both curved surfaces and linear surfaces. So if you are, or flat surfaces, if you're looking at an example like that, it really depends on which variable is being changed. And your volume formula here for your cylinder is going to be pi r squared h, right? And like I said earlier, it doesn't matter if it's a two-dimensional shape or a three-dimensional shape, the idea is the same. So if I change the height, okay, so if the height is changed by a factor of, let's say, 5, okay, so it'd be what happens to the volume if the height is increased by a factor of 5. Well, looking here on my volume formula, h, that's just a single variable, right? I don't have any exponent. So if I increase the height by 5, then the volume would increase by 5. However, if I asked you a similar question for the same example, what happens to the volume if the radius is increased by a factor of 4, for instance? Well, the radius in this equation does have an exponent, radius squared. So when I plug a radius that is 4 times bigger than the original, it's going to be 4 squared times bigger, or 16 times bigger. Okay? Keep that in mind as you're going through this section. Another just kind of tidbit that you can always do, what I would do, let's say I didn't remember this unit. You can always plug and chug and try to experiment and see what you get. And that's kind of what I would recommend if you get stuck on something like this. So let me give you an example here. Let's use the same circle example. So it says, what happens to the area of a circle if the radius is changed by a factor of 1/2? So maybe I forget the concept. I would just throw out a number. Let's say 10, right? So my original radius for the circle is going to be 10. So that would be pi times 10 squared, which is 100 pi. And remember to put your units if they're given. So, okay, what happens if that radius is changed by a factor of 1/2? Well, half of 10 is 5, and 5 squared is 25. So just kind of using like a sample point to plug and chug and test it out, I can see, right, it didn't get 1/2 smaller, right? It got reduced to a factor of 1/4, not 1/2. That's all for this section. If you guys need help, reach out to me, but otherwise, have a good day.